Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to discuss about Zener Diode. So what exactly is a Zener Diode and in what way it is different from normal PN junction diode, and we talk about its VI characteristics, and then there is one important mechanism in Zener Diode, and we try to see what is the difference between normal breakdown and Zener breakdown. And then in the end, we are going to see one application of Zener diode, where Zener diode it is used as voltage regulator. So that also we are going to discuss today. So before starting about Zener diode, first let us have brief introduction about what exactly is a PN junction diode. We know that when we talk about PN junction diode, so if we take our PN junction diode, so here generally how we will form PN junction, what we are going to take, we are going to take two types of extrinsic semiconductors. So first we are going to take P-type semiconductor, right? And here we have our P-type semiconductor, and then we are going to take N-type semiconductor. And when this P-type and N-type semiconductor are joined together, then of course that particular junction, it is, or that particular system, it is called as PN junction. And what is the other name for this PN junction? This PN junction, it is also called as junction diode. And generally when we talk about symbol of junction diode, it is represented by a triangle and then followed by vertical line. So this is the symbol of diode. And when we talk about what happens when PN junction is formed, we know that when we take P-type semiconductors, which are generally formed by adding travelent impurities to intrinsic semiconductor. And here, what we are going to observe here is these travelent impurities, they have this tendency of accepting electron from valence band of intrinsic semiconductor. So that's why this P-type semiconductor, they have majority charge carriers as holes, and they have a very few number of electrons. And when we take N-type semiconductor, in N-type semiconductor, what we are going to observe here is we are going to add pentavalent impurities, and these pentavalent impurities, they have this tendency of donating their electron to conduction band of intrinsic semiconductor. As a result, the majority charge carriers are electrons, right, and the minority carriers are holes. And once we combine this PN junction, once PN junction is formed, then what we are going to observe here is here diffusion as well as drifting. There are two processes involved here. One is diffusion of charge carriers, and second one is drifting of charge carriers. First, diffusion of charge carriers takes place. And what exactly is diffusion? Because of diffusion, we'll have flow of charge carriers from higher concentration to lower concentration region. And here in P-type, we have a higher concentration of holes, whereas in N-type, concentration of holes is minimum. So that's why we'll have flow of holes from P-type to N-type semiconductor. And similarly, in N-type semiconductor, we have majority of electrons, whereas in P-type, we have minority. So that's why here also electrons, they start flowing from N-type to P-type, that is from higher concentration to lower concentration. And what we are going to observe here is this diffusion of charge carriers. Once it is taking place, then in general, when holes from P-type, when they go to N-type, they combine with electron, so, and they will lose their energy and they'll become neutral. Similarly, when electrons from N-type, if they go to P-type, they become neutral with holes in P-type. They lose their energy and they'll also become neutral. And because of this, a region is formed at the junction, which is combining both P-type and N-type semiconductor. So this is our depletion layer. And if this is our P-type semiconductor and if this is N-type semiconductor, of course here we have majority charge carriers holes, and here we have majority charge carriers electrons. So we know that diffusion of electron is taking place. And of course, this is the layer which is separating P-type and N-type semiconductor. Then what we are going to observe here is this hole, when it goes to N-side because of diffusion, it will lose its energy to electron in inside, and then it will become positively charged ion, and of course we call them as immobile positive ions. So they are called as immobile positive ions, which do not have any energy, Okay, so these are the charge carriers without any energy. We can also say that these are holes without any energy. Similarly, when electrons from N side, when they migrate to P side, so what they are going to do, they'll combine with holes there, they'll become neutral, and they'll also lose their energy, and they will form negatively charged ions. So now these are immobile negative ions. So these are our immobile negative ions, right? So as you can see, at equilibrium, we have these immobile ions. There is formation of positively charged ions towards the N side, and there is formation of negatively charged ions at the P side. And because of this charge separation, a voltage will be developed across the layer, and that voltage it is called as barrier potential. So that particular voltage it is called as barrier potential. And what is the role of this barrier potential? This barrier potential it is going to stop further diffusion of charge carriers. So there won't be any further diffusion of charge carriers. So diffusion process will stop here itself because of formation of this voltage, which will prevent the flow of charge carriers across the junction. And this particular region where there is formation of barrier potential, that region it is called as depletion layer, because it does not consist of mobile charge carriers. So it consists of immobile charge carriers. So that's why this is the layer which is depleted of free charge carriers. That's why it is called as depletion layer. And what we have seen here is when we take this such PN junction diode and when we bias it. So when we talk about biasing of PN junction, so when we talk about biasing of PN junction, then what we are going to observe here is there are two types of biasing. Generally, biasing it is done in two modes. Biasing is nothing but when we apply external voltage to PN junction diode. So that biasing can be done in two ways. One is forward biasing and second one is reverse biasing. What is forward biasing? Where P type of PN junction it is connected to positive terminal, and N type of PN junction it is connected to negative terminal. And we know that once we forward bias PN junction, then what we are going to observe here is this width of depletion layer it is going to decrease, because as we can see, holes they get repelled by this positive terminal of battery and they start moving towards the depletion layer. Similarly, electrons they suffer repulsion from negative terminal of battery and they will also start moving towards the depletion layer. And as you can see here, whatever mobile charge carriers are there in the depletion layer, they will also gain energy because of this forward biasing, and the width of depletion layer slowly decreases because all these mobile charge carriers will become mobile and they'll take part in conduction. And what we are going to observe here is when we keep on increasing voltage, suppose if we take variable forward voltage, then there exists one particular voltage. At that voltage, this depletion layer is completely eliminated. Okay, and then once depletion layer is completely eliminated, then there is no prevention of flow of charge carriers. That's why we'll have large current flowing across the junction. So here completely it will act as conductor, and that particular voltage where depletion layer is completely eliminated, that particular voltage it is called as threshold voltage, new voltage or cut-in voltage. Now this is one type of biasing, and talking about another type of biasing which we are going to use it in our today's topic, which is Zener Diode. So when we talk about this other type of biasing, which is reverse biasing, where we are going to connect this P type of PN junction to negative terminal, and N type of PN junction we are going to connect it to positive terminal. Now, as I told you, this reverse biasing we are going to discuss here, and it is very important, and how it is going to play a very important role in Zener diode we are going to see here. So again, coming back to this PN junction where we have P type and this N type. So this is our P type, and of course here we have our depletion layer, which consists of immobile charge carriers. So these are our holes, and of course these are our electrons. As you can see, these are our electrons. And when we talk about this reverse biasing, so once we reverse bias a PN junction, then what we are going to observe here is what is reverse biasing, where P type of PN junction it is connected to negative terminal of battery, and N type of PN junction it is connected to negative terminal of battery. N type of PN junction, it is connected to positive terminal of battery. Now as we know that holes, because they are positively charged, so they have attraction towards the negative terminal of battery, and similarly these electrons, they have attraction towards the positive polarity, and they'll also have attraction towards the this positive terminal of battery. And because of that, what we are going to observe here is these holes and electrons, they move away from the depletion layer, so width of depletion layer will increase. And when there is increase in the depletion layer, and because all our charge carriers, they are losing their energy, so that's why there is no flow of current. So that's why our junction diode, generally it will be acting as a insulator once we reverse bias it. Actually what we are going to observe here is it's not completely zero current flowing in reverse biasing. There is small current, and that current is called as leakage current. So during reverse biasing of PN junction diode, there is small current flowing across the PN junction, and that current, it is called as leakage current. And what exactly is leakage current? Current produced because of flow of minority carriers. So we know that apart from majority charge carriers, if we take P type, so of course majority charge carriers are holes. Apart from that, it has got minority carriers, electrons. And whereas if we take N type, majority charge carriers are electrons and minority charge carriers are holes. And these minority charge carriers, they are going to produce small current when we reverse bias PN junction, and that current, very small amount of current, and that current magnitude, it comes in microamps. And that small, actually this current, it is also called as dark current. So this current, of course, very small current during reverse biasing, and that is leakage current due to my flow of minority charge carriers. And generally we'll say that during reverse biasing, our diode will act as, of course, insulator. Now, of course, when we try to take VI characteristics of PN junction diode, now why I have to talk about this again? Because when we talk about Zener diode, we are going to compare with PN junction diode, and we are going to see how it is far better than our normal PN junction diode. And if we take our normal PN junction diode, we have this problem of having very less current flowing across the PN junction when it is reverse biased. And that problem we are going to overcome in this Zener diode. And when we talk about VI characteristics of normal PN junction diode, so if I take normal PN junction diode, so when I take its, of course, VI characteristics, so when we take normal PN junction diode, and when we talk about its VI characteristic, suppose if I apply for the forward voltage, then we have our forward current flowing across the junction, and that current, it comes in milliamps. And initially with increasing voltage, current will be very, very negligible, right? And after that, at one particular voltage, so there exists one particular voltage, as I told you, that voltage, it is called as threshold voltage or knee voltage. And at this voltage, what we are going to observe here is there is sudden rise in the current because depletion here is completely eliminated. Whereas when we go for reverse biasing of PN junction, so when we are applying voltage in the reverse direction, if this is reverse voltage, then as I told you, very small current will be flowing across the junction diode, and that too because of minority charge carriers. So this is a reverse current, and it is in microamps. And that reverse current, as we know that it is very, very small current. So here we have very small current flowing across, and this current, it is called as dark current. Okay, and it is also called as leakage current or dark current because very small amount of current will be flowing. Now our purpose is to make a reverse bias PN junction diode conducting, and that we are going to do in Zener diode. So what exactly happens in the Zener diode? Now coming back to a Zener diode, if you look at the Zener diode, so this Zener diode, of course, as I told you, it is specially designed in order to make a reverse biased diode conductive. So that's why we call it as specially designed diode. And this diode, what it will do, it is going to operate. What do you mean by it is going to operate? It is going to conduct current even in reverse biased conditions. So it is going to conduct current even in reverse bias conditions. And generally, how we'll make the Zener diode? Generally, if you take our normal junction diode, in normal junction diode, when we combine p-type and n-type semiconductors, so we are not going to heavily dope them. So we have just less number of impurities being added to intrinsic semiconductor in order to make them p-type and n-type. But when we are taking p-type and n-type semiconductors in Zener diode, we are going to heavily dope them compared to ordinary diodes. What do you mean by heavily doped? So if I take p-type, in that p-type, I'm going to add very large amount of travelent impurities, and if we go for n-type, in n-type we are going to add very large amount of pentavalent impurities. So doping is done. So very large number of doping is done compared to ordinary diodes. And one thing what we have to understand here is, when we take our normal diode, in normal diode we are going to have thick depletion layer. So what is a depletion layer? At the junction which is separating p-type and n-type, there will be formation of one layer, and that layer, it consists of mobile charge carriers, and the width of the depletion layer in normal diode, it will be thick. But if we are forming a diode, and the diode, in the diode, if we take p-type and n-type semiconductors, if they are heavily doped, then they are going to have narrow depletion region. Okay, and here, of course, what is the main advantage of having narrow depletion region, and in what way it is going to benefit us, in what way it is different, not only about the construction, but when we talk about its working, how it is different from normal diode, we are going to see in next slide. And as I told you, in the end we are going to focus on its one of the application. What is that application? Where it will be working as voltage regulator. Now, first, we are going to just take introduction about the Zener diode, and what is the other name of Zener diode? Zener diode is also called as breakdown diode. Okay, why it is called breakdown diode? Because generally every diode, if you take our normal diode, this normal diode, when we are going to apply reverse voltage, so there exists one particular voltage. At that particular voltage, breakdown of junction takes place. So at when breakdown of junction takes place, then our diode, it is going to get damaged, and we cannot use this diode for next application. Okay, so usually we'll try to avoid using our normal diode in breakdown voltage. So actually in normal diodes, this breakdown voltage, it occurs at very high reverse bias voltage. And what happens at breakdown voltage? Of course, what we are going to observe here is, whatever electrons are there which are taking part in covalent bond formation, electrons, atoms of intrinsic semiconductors, and those atoms, their electrons which are taking part in covalent bond formation, so they are going to gain kinetic energy, and these electrons, they'll come out of their bond, and they give rise to very large reverse current. Even though there is increase in the current, so generally when we draw this VI characteristic, what we are going to observe is, of course, initially till very high reverse bias voltage, very small current flows. But when I go to very high reverse bias voltage, then what we are going to observe here is, there will be increase in the reverse current. Okay, and this occurs at one particular voltage, and that voltage, it is called as breakdown voltage. So it is called as breakdown voltage, where diode is going to break down. And what do you mean by breakdown? Suppose if I take this p-type or n-type semiconductor, suppose I have taken p-type semiconductor. We know that in p-type semiconductor, what is the impurity we are adding? We are adding boron impurity, and boron, it has got 3 valence electrons. Out of those 3 valence electrons, it is going to form 3 covalent bonds with adjacent silicon atoms. Whereas, of course, in the fourth bond, one position is vacant, so it will try to accept electron from adjacent silicon atoms. Now here, if you will observe that this hole, it is going to take part in conduction. But if I go to such very high breakdown voltage, whatever electrons, see here, if I look at the other positions of intrinsic atoms, all their electrons, they are taking part in covalent bond formation. Now, at very high reverse bias voltages, they will gain enough energy, enough kinetic energy to break their bonds. They'll come out of their bonds, and they'll move freely, giving rise to large reverse current. So like this, we'll have many covalent bonds. So all those bonds will break, and there are so many number of electrons coming out, giving rise to large saturation current. Of course, here we are getting large saturation, large reverse current. But what you're going to observe here is, if I go to such high reverse bias voltage, then our diode, it is going to get damaged. And once it is damaged, we cannot use it again for the next time. So that's why generally we'll avoid normal diodes to operate at such high reverse bias voltage, which is called as breakdown voltage. But here, what we are going to do here in Zener diode is we'll construct it in such a way that I try to achieve this breakdown voltage at low reverse bias voltage. I'll try to achieve this breakdown voltage at low reverse bias voltage in case of Zener diode. That is what we are going to do in Zener diode. So here, as I told you, of course, that's why it is called as breakdown diode. And as I told you here, p-type and n-type semiconductors, they are heavily doped. And of course, it is taken as a device. And of course, this device, it is operated in reverse direction. And our intention is to increase reverse current. And once we, of course, Zener diode is reverse biased, then as I told you, we try to bring down this breakdown voltage value. Suppose if it is some 1.5 volts in case of normal diode, then if we come to our reverse, when we come to our Zener diode, it can be come down to 0.5 volts. So at this 0.5 volts, you'll observe that there is increase in reverse saturation current. So, and this particular voltage at which breakdown takes place in Zener diode, that particular voltage, it is called as Zener voltage, or it is also called as knee voltage, where current starts flowing across reverse biased diode. And this effect, it is called as Zener effect. And as you can see, if we take to our normal diode, it does not allow any current to pass through it in reverse direction. It blocks current in the reverse direction. And also, if you go for high reverse bias voltage, it will go to premature breakdown or damage when we go for very high voltages, right? And coming to this Zener diode, as we told you that this diode, it is formed with heavily doped p-type and n-type semiconductors. And what is the general symbol for Zener diode? This is our symbol. And if we try to compare with our normal diode, so generally what we'll do, we'll draw one triangle and then it is followed by one vertical line. So this is our normal diode. But once we try to give symbol for Zener diode, what we are doing, this vertical line, it is kept like this in order to differentiate between Zener diode and of course our normal diode. And of course this triangle, it represents anode. And whereas this vertical line, Z type of vertical line, it will represent the cathode of the Zener diode. This is about the symbol of Zener diode. Now we are going to discuss about Zener diode circuit diagram. Okay, so as you can see, this is our PN junction. Okay, and this PN junction, it is heavily doped, where we are going to add very large amount of impurities. So here p-type, it is doped with large amount of travalent impurities, whereas n-type, it is doped with large amount of pentavalent impurities. And when we compare with normal PN junction diode, because here they are going for very heavy doping, so that's why we'll observe that depletion region is thin. So what is the difference here? We can make out two difference between normal diode and Zener diode. So in normal diode, doping is light, and whereas in Zener diode, doping is heavy. And when we take normal diode, depletion layer is thick, and whereas in Zener diode, because of heavy doping, our depletion layer is thin. Because here there are plenty of charge carriers taking part in conduction, and depletion region is the region where we have charge carriers without energy, which is depleted of charge carriers. Right, and of course, as we told you that Zener diode, it's a reverse bias diode. So as you can see, when we form circuit, so here if we take n-type of PN junction, it is connected to opposite polarity. It is connected to positive terminal of battery. And this p-type of heavily doped PN junction or Zener diode, it is connected to negative terminal of battery. So n-type material, it is connected to positive terminal, and p-type material, it is connected to negative terminal of external power supply. And of course, our depletion layer is very thin because it is very heavily doped. Now, we are going to see how the Zener diode is going to work. If you look at these figures, two figures which are given in the slide. Now, what I have done, I have of course reverse biased Zener diode. As we know that this p-type, it is cathode, or it will act as a positive end, and whereas this this line, it will act as negative end of the diode, and this negative or n-type of this Zener diode, it is connected to positive terminal of battery, and this of course p-type of Zener diode, it is connected to negative terminal of battery. And of course our voltage, it's a variable voltage, so where we are going to increase our voltage in steps. And what we are going to observe here is, in this case, what I have done, slowly I started increasing reverse bias voltage. Then what you're going to observe here is, there won't be any current flow across the Zener diode until, okay, your voltage does not exceed Zener voltage. So in this case, if I take my Zener voltage, which is defined as Vz, so if your applied voltage is less than the Zener voltage, then there is no flow of current across this circuit, where we are putting one resistance in order to make flow of current. But whereas in the second case, what we are going to observe here is, here our applied voltage, it has gone beyond our, at least it is equal or it is greater than or equal to our Zener voltage. So once our applied voltage, it is crossing Zener voltage of this particular Zener diode, then what happens here? So what we are going to observe here is, breakdown takes place, and here there will be increase in the intensity. So there will be formation of electric field across the depletion region, and there will be increase in the intensity. So that's why you'll observe that there is a flow of current across the Zener diode. So here, as you can see, here is our main purpose of heavily doping is in order to increase high level of impurities, which will make our diode conductive. And of course, depletion layer is thin. And one more thing, what we have to understand here is, because of heavily doping material, it is going to increase intensity of electric field across the depletion region, even at very small reverse bias voltage. This is very important point. So what we are saying here is, because of heavy doping of PN junction, what we are going to observe here is, intensity of electric field, it is going to increase across the depletion region, even for small reverse voltages. So in order to make Zener diode conductive, we have to go for voltage, okay, applied voltage greater than or equal to Zener voltage. Now, so if we try to understand more about the Zener diode, suppose when there is no biasing across the Zener diode, then of course what we are going to observe here is, the electrons of the valence band easily move from one, like when we talk about forward biasing, and then of course we come for reverse biasing. When we forward bias, actually when we don't bias our Zener diode, there won't be any flow of current. And when we forward bias reverse diode, this Zener diode, then what we are going to observe here is, it will just work like normal ordinary diode. So we can understand this concept of characteristic of Zener diode. Right, so as you can see here, first, when there is no biasing applied across the Zener diode, then we are saying that electrons, they don't get any energy, so that's why there won't be any flow of current across the diode. And what we are going to observe here is, but when we forward bias it, then what happens? There will be flow of current, it will just behave as normal diode. Whereas when we reverse bias a diode, and when we cross our applied voltage or supply voltage beyond the Zener voltage, then breakdown takes place, depletion region completely vanish, and we have our current flowing across the reverse bias diode. So, and why there is increasing current? Because intensity of electric field across the depletion region is going to increase. And because of increase in the intensity of electric field, we are going to observe that it allows electrons to move from valence band of p-type material to the conduction band of n-type material. So there will be movement of electrons from valence band of p-type material to the conduction band of n-type material, and this transferring of electrons, they give rise to current. So they will make reverse bias diode conductive. And to understand it better, we are going to take VI characteristics of Zener diode. And if we consider VI characteristics of Zener diode, what we are going to observe here is, in this particular figure, if I take our Zener diode and if we forward bias it, suppose if this is our Zener diode, and what we are doing to the Zener diode, it is being forward biased. So forward biasing is nothing but where we are going to apply P-type of diode to positive terminal of battery, and N-type of diode is connected to negative terminal of battery. So in such case, we know that slowly first there is small current flowing across the Zener diode, and once we come to a voltage, and what is this voltage? This voltage, it is called as threshold voltage or knee voltage. So this is called as threshold voltage or knee voltage, or it is also called as cutting voltage. So knee voltage, or it is also called as cutting voltage, where depletion layer is completely eliminated and we have large current flowing across the Zener diode. So as you can see that when we forward bias Zener diode, it will just work as a normal diode. But when we reverse bias Zener diode, as you can see, if we try to compare with normal diode, there is small amount of current flowing. So here also, if I take Zener diode at a low reverse bias voltage, what I mean by low reverse bias voltage, where supply voltage is less than our Zener voltage, so there is negligible current flowing across the Zener diode. But once I come to a voltage called as knee voltage, it is also called as breakdown voltage, it is also called as Zener voltage. And what happened to our reverse current? There is sudden increase in the reverse current. And what happens at this Zener voltage? As we know that there will be increase in the intensity of electric field across the depletion region. Okay, so here, as you can see here, once we take this, of course, when we reverse bias it, and if reverse voltage goes beyond one particular value, then Zener breakdown takes place. What is Zener breakdown? Where there is sudden rise in the reverse bias current. And generally at Zener breakdown voltage, what happens? Current starts flowing in the reverse direction. And what you're going to observe here is, of course, if we consider the Zener breakdown, it is not exactly vertical. So it means that the Zener diode has some resistance. So as you can see, it is not vertical. Okay, so it indicates that Zener diode, it has got some resistance. And if we try to figure out what is the voltage across this Zener, then we can write it as Vz. So of course Vz is our Zener voltage, and this is the Zener current that is flowing at that particular voltage, and Rz is the resistance given by Zener diode. So this is the graph given by our Zener diode. Now when we try to compare between normal diode and Zener diode, I think this graph, it is going to eliminate all our questions or all our doubts arising related to Zener diode. So talking about this, now we try to compare Zener diode with ordinary diode. As I told you, when we forward bias Zener diode, it will work as normal diode. So as you can see here, so characteristic, it will be same for ordinary diode as well as Zener diode. So as you can see, first initially current is 0, and once we reach threshold voltage, there is sudden rise in the current, and this current, it is going to come in milliamps. And here depletion, because depletion layer is completely eliminated, so there is sudden rise in the current. Now we try to figure out in reverse biasing. So as you can see, there are two curves. This curve, it is exhibited by Zener diode. So this curve, it is exhibited by Zener diode, whereas the second curve, it is given by ordinary diode. Now, what is the difference between the reverse curve exhibited by normal diode and Zener diode? Now, as you can see here, in both the cases, when we are at very low reverse bias voltage, very small current is flowing across the Zener diode. And of course, this current, it is called as leakage current, which is the current due to minority charge carriers. So very small current is flowing. First, I'll see for normal diode. Now, as you can see, even though we are increasing reverse bias voltage, there is no increase in the reverse current, and this reverse current, it will come in microamps. So this reverse current, it will come in microamps. And when I go for high reverse bias voltage in case of ordinary diode, see here, this is very high reverse bias voltage. So this value is very high. So we'll take it to be high reverse bias voltage. And when we go for such high reverse bias voltage, what we can observe here is breakdown. And that breakdown, it is called as avalanche breakdown. What is avalanche breakdown? Where we have multiplication of charge carriers. And why this multiplication of charge carriers is taking place? Because of breaking of covalent bonds that are formed by intrinsic atoms with their adjacent intrinsic atoms. Okay. So here, all those bonds will be break, and all those electrons, they'll gain electric energy and they'll start conducting. So that's why there is sudden increase in the current. But what is the problem with normal diode? Normal diode is when we go for such high reverse bias voltage, then what we are going to observe here is our diode, it is going to get damaged. Our diode, it is going to break down. So here, because of damage, this diode, like we cannot use it again for our application. Okay, so that diode, it is permanently damaged. Now, coming to Zener Diode. What we have done in Zener Diode? In Zener Diode, we have heavily doped it. Okay, we made our depletion layer thin. So, because our depletion layer is thin, so what we are going to observe here is that giving kinetic energy to those electrons which are involved in covalent bond formation. So that voltage, it will be very less voltage. So as you can see, this breakdown in case of normal diode, it is occurring at very high reverse bias voltage. But whereas when we compare with Zener diode, so as you can see, this breakdown, it is taking place at low reverse bias voltages. So it is taking place at low reverse bias voltage. So as you can see, it is taking place at low reverse bias voltage. Even when we are at low reverse bias voltage, breakdown has taken place and there is large amount of reverse current flowing across the junction. It means that our diode, it is acting as a conductor even at low reverse bias voltage, which is not possible with ordinary diode. So that's how we are going to make our Zener diode conductive at low reverse bias voltages. I hope, like there is a clarity between what is Avalanche Breakdown and Zener Breakdown, and in order to make it more clear, we can observe these points. So when we talk about Avalanche Breakdown, which is taking place in normal ordinary diode, and when we talk about Zener Breakdown, which is taking place in Zener diode, and those two phenomena, they are two different mechanisms which are exhibited by a PN junction when it breaks. And of course, both these phenomena, they are taking place when our diode is reverse biased. And here, as you can see, this avalanche breakdown or the breakdown which is occurring in normal diode, it is because of ionization of electron hole pairs. What is ionization of electron hole pairs? Suppose if I take our silicon atom and if we take our pentavalent impurity, and this pentavalent impurity, it has got 5 valence electrons. Out of those 5 valence electrons, it is forming 4 covalent bonds with adjacent silicon atoms. So it is forming 4 covalent bonds with adjacent silicon atoms. Now what we are going to, for conduction, of course, this electron is going to play a role. But what we are going to observe here is in avalanche breakdown, when we go for high reverse bias voltage, all these electrons which are there in covalent bond formation, they'll come out of their bonds because they are going to gain large kinetic energy, and then there will be jumping of electron from valence band to conduction band. This is nothing but generation of electron hole pair. So that's why there is increase in the current. But because we have so many number of electrons involved in such covalent bond formation, all those electrons at a time, they are going to come out. So that's why because of that large current, our diode, it is going to get damaged. Whereas a Zener breakdown, what is Zener breakdown? Where there is increase, or where we are giving this kinetic energy to all those electrons, we are doing it, and what we are going, which charge carriers are going to get this kinetic energy? Charge carriers which are generated because of heavy doping of Zener diode. So if you take a Zener diode, because of heavy doping of Zener diode, whatever charge carriers are there, they are going to gain energy, and they are going to gain energy at low reverse bias voltage. That difference we have to understand. So between the normal diode and Zener diode. So as I told you, avalanche breakdown, it occurs in normal diode, and it is because of ionization of electrons. And of course, in normal, if I take diode, here width of depletion region, it is going to change with reverse bias voltage. Now, whereas as I told you, when we talk about Zener, and of course, when we talk about ionization process in avalanche breakdown, what we are going to observe here is, in case of avalanche breakdown, here, first, these charge carriers, first minority charge carriers, they'll gain energy, and these minority charge carriers, they are going to collide with atoms of the crystal. That is nothing but electrons which are taking part in bond formation, and due to this collision, these charge carriers, they'll make those covalent bonds break, they'll make those electrons to come out, resulting in the formation of electron hole pairs. So that's why there is large amount of current flowing, which is going to break our junction, and our diode, it will be completely burnt off. Whereas when we talk about Zener breakdown, so in Zener breakdown, first thing what we have done, we have heavily doped p-type and n-type semiconductors, and width of depletion layer is very small. And what we are going to observe here is first the Zener breakdown, it occurs because there is thin depletion layer, and this thin depletion layer, it consists of more number of free flowing charge carriers. Why it consists of more number of free flowing charge carriers? Because we have given lot of holes to p type and we have given lot of electrons to n type. And how we have given lot of holes to p type and lot of electrons to n type? By adding lot or large amount of travalent impurities to P8 and by adding large amount of pentavalent impurities to N type. So that's why here depletion region, it just like our normal diode, in like if we take our normal diode, there we have many immobile charge carriers. But here in this case, depletion region, it is thin and as well as it consists of more number of free electrons. And so once we reverse bias it, there will be increase in the intensity of electric field across the depletion region, and because intensity of this electric field is very high, it is going to provide kinetic energy at low reverse bias voltage. This we have to understand. So whatever process is taking place at high reverse bias voltage in normal diode, that process it is going to take place at low voltages in case of the Zener diode. So here kinetic energy, and because of this kinetic energy, these carriers, they start jumping from valence band to conduction band, or simply we'll say that there is jumping of charge carriers from one region to other region. So, and because of these energetic charge carriers, they collide with the atoms of p-type and n-type material and they produce electron hole pair. And of course, we know that there is one voltage at which depletion region is completely eliminated, and we have our large reverse current flowing, and that particular voltage, it is called as Zener voltage, or it is also called as Zener breakdown. And we can conveniently go to Zener breakdown in Zener diode. Why? Because this Zener breakdown, it is occurring at low reverse bias voltage, which is not going to damage our diode, or our junction will not get damaged. And once we remove our reverse voltage, then what we are going to observe here is this depletion region, it is going to regain its original position, and very conveniently we can use the Zener diode for our next application. Okay. So till now we have seen how this Zener diode it is becoming conductive even in reverse bias condition. So now we are going to discuss, in order to understand functioning of Zener diode better, we are going to take one application of Zener diode where Zener diode is going to act as voltage regulator. I think we people use voltage regulators in our day-to-day life. So if there are any fluctuations in input voltage, in order to make our particular device not getting damaged, so what we are going to do, we are going to make use of this voltage regulator. No matter there are fluctuations in the input voltage, our output voltage will be constant. So now we are going to see how the Zener diode, it is going to act as voltage regulator when it is reverse biased. And as you can see here, the Zener voltage, it is going to play a very important role. So we know that what exactly is our Zener voltage? It is the voltage, and of course this voltage, it is occurring at a very low level of reverse bias voltage. And what we are going to observe at this, when we go back and when we see about this Zener voltage, we have seen that at this Zener voltage, as you can see, Zener breakdown is taking place. And what exactly happens at Zener breakdown? We have seen that first of all, these minority charge carriers which are conducting in reverse mode, they are going to gain kinetic energy and they are going to increase electric field intensity across the depletion region. And these minority charge carriers, they will start jumping from valence band to conduction band, thereby generating very large amount of electron hole pair. So we are going to have plenty of holes in valence band, and also we are going to have plenty of electrons in the conduction band. And because of this, what we are going to observe at low reverse bias voltage, we are going to get our depletion region completely eliminated. So that's why there will be increase in the reverse current. And as I told you that where we take normal diode, so for breakdown to take place, in order to increase our reverse current, we have to go for very high reverse bias voltage, which is going to spoil diode. But that problem we are going to overcome in Zener diode. So in this case, what we are trying to do, of course, here also we are giving energy to our charge carriers. But these charge carriers are plenty in number in Zener diode because of heavy doping. And here, one more thing, what we have to, as I told you that there we have to go for high reverse bias voltage. But here, we are going to low reverse bias voltage, which is not going to spoil our junction at all. So that's why once we take out our reverse bias voltage, our depletion region, it is going to regain to its original position. So that property we are using in order to regulate our voltage. So here, what exactly is our voltage regulator? So as we know that every Zener diode, it will have one particular value of Zener voltage, and we have to go beyond this Zener voltage in order to make our reverse bias diode conducting. So there is one specific voltage, okay, and of course that voltage, it is called as Zener voltage, or it is also called as breakdown voltage. And what we have to do, we have to make our Zener diode function only at this particular breakdown voltage or Zener voltage. So always our supply voltage, it has to be above this breakdown voltage or Zener voltage. And as I told you, when we have seen a VI characteristic of Zener diode, when we forward bias Zener diode, it will work as normal diode, where we see that there exists one particular threshold voltage, and when we go beyond the threshold voltage, our forward bias diode, it will act as a conductor. So the functioning of Zener diode, it will be same as normal diode when we forward bias a diode. But when we go for reverse biasing, in order to make our diode conductive, what we have to do, we have to go beyond the Zener voltage, and the Zener voltage, it is represented by V setter. Okay, so when Zener diode is reverse biased, and if our voltage is less than the Zener voltage, then what will happen? There is no flow of current, or we can say that there is flow of very leakage current, and that current, it is because of minority charge carriers. So in order to go for large amount of current, then what we have to do, we have to go beyond this Zener voltage. Then our voltage is limited. So here we have to stop near the Zener voltage. So once we go to the Zener voltage, then we have automatically large amount of current flowing. So that's why what exactly we are doing at this particular position, we are limiting our voltage and this property. And of course, at this limit voltage, what exactly is happening? There is flow of large current, and this property, it is used in voltage regulator. So what is the property which is going to help us in using this Zener diode as voltage regulator? So what we are going to do, we know that there exists one voltage, Zener voltage. At that Zener voltage, we are going to limit our voltage and there is large amount of current flowing across it. And if what we are going to do, we are going to place our Zener diode in parallel with one of the resistors. Generally, this is the construction of any voltage regulator. So in a voltage regulator, what we are going to do, we are going to take Zener diode and we are going to place it in parallel with one of the resistor, of course in a voltage divider circuit. Then of course no current flows through the Zener diode when its voltage is less than the breakdown voltage. But once we go to voltage equal to Zener voltage, then what happened? Now current starts passing through the resistor and the rest it will pass through the diode, and this results in our constant voltage. So voltage remaining constant, and if the input voltage increases, then current through the voltage divider, it is going to increase, and then what we are going to observe here, there is increase in voltage across the other resistor. So we can try to explain this using the circuit diagram which is given in this PPT. Now here, as you can see, the exciting part of the diode is we can use a Zener diode in breakdown voltage which is less. Now we try to talk about the Zener voltage by taking one particular Zener diode and taking its one particular Zener voltage value. So here I have selected a Zener diode which has got its Zener voltage at 12 volts. So that's why this particular Zener diode it is used in order to limit our voltage to 12 volts. So we can make use of this Zener diode as voltage regulator, which will not allow voltage to go beyond this 12 volts. Okay. Now how it is going to function, we are going to explain it using the circuit diagram. So if you look at this circuit diagram, this is our variable input supply. This is our supply voltage. And here we have our resistor, series resistance. Okay. And then of course, this is our Zener diode. And there is one more resistor in parallel to Zener diode. This is a load resistor and this is series resistor, and this is our voltage, which is nothing but Zener voltage, because here I have used Zener diode which has got Zener voltage equal to 12 volts. So this voltage regulator, it can be used in order to give steady voltage equal to 12 volts. So as you can see here, first of all, we have a Zener diode which is connected across this load resistor. So here we have one resistor parallel to Zener diode. And apart from that, we have one more resistor, series resistor, okay, which is connected in series to Zener diode. And if you want to regulate our voltage across this diode, and it should not cross beyond this Zener voltage. So what we are going to do, we are going to choose our Zener diode which is having breakdown voltage depending upon our voltage, constant voltage, right? And also we are going to choose our load also. So requirement of the load depends upon the Zener breakdown voltage. So as you can see, of course, here we have our Zener diode. It is reverse biased, and once we go to voltage beyond the Zener voltage, then we know that Zener diode, it will make large current flow across the diode. And because this load is in parallel to the diode, then what we are going to observe here is voltage drop across the diode. It is equal to Zener breakdown voltage. So it will provide a path for the current to flow. Hence the load gets protected from excessive currents. So that's why not only the Zener diode, it will act as a voltage regulator, but also it protects the load from excessive current. So here, different diodes, different Zener diodes, they are used for different voltage regulations, and that depends upon the Zener voltage values. And always when we have to use them, we have to connect to one resistor in parallel to this Zener diode. So whenever it exceeds, of course, Zener voltage, then what this load resistor will do, this load resistor, it will provide a path, and of course, there won't be any flow of excessive current across this load. So today in this particular video, we have discussed about one specially designed diode in order to work or to make it work, making large current flow across it in reverse bias condition. And we have seen that how the Zener diode is different from normal diode. And then we tried to compare VI characteristic of normal diode with Zener diode, and we came to know difference between Zener breakdown and Avalanche breakdown. And in the end, we have discussed one important application of Zener diode as voltage regulator. I hope this video is helpful for you to understand about Zener diode. I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.